I want to explain the image that you're looking at right now, which is known as Newton's fractal. A little more accurately, it's an infinite family of fractals, and aside from being this beautiful, mesmerizing, infinitely detailed mess, what's really cool about the image is how it naturally pops out from something that any of you who've taken a calculus class might have heard of, known as Newton's method. A lot of math is about solving equations, and Newton's method is a really powerful tool for finding approximate solutions to essentially any equation. If you rearrange the equation so that it looks like setting some function of x equal to 0, then visually what it means to solve such an equation is to find a point where the graph of that function crosses the x-axis. Now, the way that Newton's method works is to start by making an arbitrary guess. And of course, the guess is almost certainly not a solution. But if you draw a tangent line to the graph at that guess, and you ask, where does that tangent line intersect the x-axis, something much easier to solve explicitly, very often it takes you closer to a true solution. If you wash, rinse, and repeat, doing this multiple different times, you often converge towards a solution especially quickly. If you do all the calculus and you work it out, there's a certain formula for how big your step size should be based on this process, and I won't go into the details, but just know that it is a formula and you can plug in one value, and what comes out is usually something closer to a true solution of the equation. For our purposes, instead of considering a function with real number inputs and real number outputs, like we're used to, consider all of the complex number inputs and the corresponding complex number outputs. Now, we can't visualize Newton's method with tangent lines and intersecting the x-axis anymore, but the formula still works. It's still a valid rule that tells you how you can adjust one guess to push it closer to a true solution of the equation. Maybe that feels a bit bizarre. I realize not everyone loves complex numbers the way I do, but here's the cool part. Watch what happens if we apply this idea to many, many different possible initial guesses. So on each iteration, each of those dots is taking a step based on this Newton's method rule. Now with the example I'm showing, where our function is a degree 5 polynomial, there are 5 distinct solutions to the equation somewhere in the complex plane. After many different iterations, most of our dots have zeroed in towards one of those solutions. What I'm going to do is color each one of those dots based on which of those 5 solutions it landed on, which one it ended up closest to, and then we'll kind of roll back the clock to see where each dot came from in the first place, giving us a certain color pattern. If you do this at a very fine resolution, treating each pixel of the screen as a possible initial guess, and going through the same game, coloring it based on which route that guess would end up landing on, the pattern that emerges is the image that I showed you at the start. Isn't that wild? There is a lot more to say about it, and if you want a less rushed explanation, on the full video over at YouTube, I talk much more about why you see a pattern like this, and what it implies about using Newton's method in practice, and how it connects to things like the Mandelbrot set. But for now, it's fun to just gawk at the beauty of math.